So this chapter deals with probably the core problem that most people face when they're wrestling with how to represent high-dimensional data. And they have to decide what mapping they would like to make. And finding the appropriate mapping is probably the hardest part of doing any visualization well. So one of the things that I think helps people make good decisions is to increase your literacy in the full scale of possible dimensional mappings. So this chapter is really going to be a high-speed walk through a number of visual mappings, focusing on a few that I think are particularly effective. So the first is this idea of small multiples. Small multiples is a name that Tufte gives to a technique that's been around for hundreds of years. And he describes them as postage stamp-sized graphics indexed by some kind of category or label. And they're sequenced over time, like the frames of a movie. And they're ordered by some sort of quantitative variable that's not part of the image itself. And what's key to small multiples is this idea that we have a repetition of form with a uniform presentation. And this allows us to focus on the differences in the images. So if you look here at this very, very wonderful early example of a small multiple, which comes from Galileo's notebooks, and I'm taking this particular example from Tufte visually, and he describes how Galileo shows Jupiter and the moons of Jupiter that are visible on consecutive nights. And what you see here is the organizing principle is a vertical axis that here represents time. But what you're able to see is that consecutively on different nights, moons appear in different locations relative to the planet. And this presentation allows you to focus immediately on the differences between each of the individual nights. And you'll see this is used again and again in science. Here's an example showing measures of atmospheric contaminants within the Los Angeles area. And what you'll see here is that actually the small multiple is organized into 3 rows. So we've taken a nominal variable, which includes the pollutant type, and allowed that to represent each of the different, that's shown on each row, and then time on the x-axis. And so what you can see is something like nitrogen oxide peaks very late, while something like hydrocarbons are peaking, are not active between midnight to 3, but very active throughout the rest of the day. So the beauty of small multiples is that this unique form of presentation allows you to quickly jump with your eye between different iterations, and you focus on the differences between each of the different measurements. So you can look at this example of trilogies, movie trilogies represented as, small multiples. And what you can see here is that each set of trilogies is shown next to one another with a little bar graph that represents the person's opinion of the different movies. And so you can see that the person found Mad Max 2 to be even better than Mad Max 1. Whereas if you look across Star Wars, they all seem to be fantastic. Whereas Jaws 1 was incredible and 2 and 3 were Small multiples gives you a wonderful way to compare, to present this data. Now, this data could be easily shown in a histogram or a line graph, but the small multiple representation allows you to cluster each of the different variants together and allow you to focus on their differences. Here's another wonderful example of a small multiple. It's lipsticks shown by artist Stacy Green. And what's wonderful about this set of small multiples is saying, well, where is the data here? Well, each one of these lipsticks is a lipstick taken from a different woman that the artist knows. And what you actually see is a portrait of the woman applying the lipstick. And so what you get to see is the way that they move their hand through space as they apply the lipstick. And you see that the woman in the middle really applies this twisting motion as she applies the lipstick, whereas the woman on the top middle pushes much harder on the bottom than the top as she moves through her. So what's beautiful about this small multiple is that you see real comparisons between each of these unique portraits of a person, but the actual data is hiding behind the image itself. Here's another wonderful example of a small multiple. Artists has taken the covers of Playboy magazine from the 60s, 70s, 80s, and 90s from left to right. And through a technique called image averaging, has averaged all of the different images through the centerfold. And what you can see is a true trend in the male historical gaze as a preference towards going from a more of a dark-haired woman to a blonde-haired woman, from more of a robust woman to a more skinny woman. If we turn to a slightly more empirical data set, let's take a look at various ways that one might compare Fisher's historical data on different types of irises. So perhaps I think easiest to see is this parallel plot. And what you see here is that each of the different dimensions, a color is used to represent each of the different nominal iris categories or types. And then an axis, a vertical axis, is used to represent each of the different features of each category. And so you can see sepal length, petal length are all represented on this scale. And then each iris is represented as a single line drawn across from axis to axis. And you can see that iris setosa clearly clusters in the bottom left and generally has a smaller petal length than the other irises, like the virginica, which has a much larger petal length. So one additional, very powerful technique for representing data is something that Tufte calls a sparkline. And it's a very small, simple, word-sized graphic. And Tufte describes it as having a typographic resolution. And what he means is these are graphics that we can embed into the very text of our scientific documents. And so if you have a number here, like for example, glucose at a level 6.6, well, in general, for many readers, this number might have no context or scale or history. So we can change this in line in the document by adding a very small line graph that would show the data value 6.6 and comparing it to earlier measurements. So what you can see now is that same number actually has a history and can show you that for this particular person, there was a peak at some point halfway through that history, and it's now more at normal levels. Another thing that one might be able to do is to tie that number, the number which we're describing in the text, to the actual line graph using a color marker. So you can see that semantically we've created a relationship between 6.6 and the rightmost number in the line graph. Another additional thing that you can do for a sparkline is to show something that includes the normal distribution. And so by using a slightly different background color, what you're now additionally able to see is not just that 6.6 is the latest value, but it's within normal range, and that peak value was only above normal range for a short period of time. So the graphic itself can be moved on either side of the actual word it's describing or the number, and that they can be embedded right into the text of a scientific document. Separately, very often we find that these types of graphs are used in things like financial pages to describe a history